we saw a lot of talks in previous days and also today where point defects appeared in several models from nematic liquid crystals, ferromagnetics, also superconductivity. Okay, and the aim of my talk is, in fact, to see how the geometry or the topology of a surface can influence on the location and structure of these vortices that will be, in fact, so in general, so I will consider several models, but in general, you should consider that these are vector fields on a Riemannian manifold, so of dimension 2. So a vector field here is in the sense of geometry, so tangent vector field. So when I say vector field, means really that the vector is tangent at the surface. So what I will present you here is technology that we put in place with Bob Gerard from Toronto in order to find the exact location, the optimal location of these vortices on a surface. And this technology, of course, existed on the flat surfaces, but here you will see a new phenomenology that will come to play, that are these kind of flux integrals that are quantized on a lattice that depends on the position of the vortices. So this is a new phenomenology in the Ginzburg-Landau type models. Okay, so let me start. So maybe during your first lesson in a algebraic topology course is the question, can you comb a surface? So what does it mean? Imagine that you have a surface, and at each point you will take a vector that is unit length. So the question is, can you comb it? So can you find a continuous vector field, so where at each point your vector becomes tangent at the surface? So the answer is no on the sphere. So always when you will try to comb it, you will see that there are several points. So in this case, in this picture, you will see 2 points where the vector will come up. Okay, so it cannot stay tangent. In some sense, this is how I explain the boldness. Why? Because you always have these frustrated barbers that do not know the topology. So they really try to comb your hair, and at some point, okay, you will have this thing that comes out like this, and then just cut it down. But when you go home, well, no hair there. So, well, this is how you can explain it, yeah? Okay, so, but, so why they, so in fact, okay, let's say that they do not like these simply connected surfaces, but they like heads with the hole, because they can do it, they can comb it, yeah? Okay, so, and in fact, these are the only surfaces where continuous tangent fields can be found. So, and the particularity of this is that you have just one hole, so what we call genus 1. Okay, so other way to see this problem is, so here we consider like maps that at each point of the surface that was considered embedded. So they are with values in S2, but if you consider the projection of this map into the tangent bundle, so the same question is equivalent by finding these vector fields that are continuous and non-vanishing. right? So this is equivalent. So in this case, so when you project this, for example, this vector, right, you get to 0. Yeah. So these two problems are equivalent. So therefore, right, I mean, when you take a vector field and you that is continuous, then you should always find the zeros there. So those zeros will come with the topological information. It's exactly like, so if you look in local coordinates and you look to a small circle around this defect point, you will see that so your vector winds the circle. So if you assume that there is no zero, and that winding number will give you what we call the degree. So now is the topology that will tell you that if you consider a vector field that has, let's say, a finite number of zeros with degrees decay, then all these degrees should satisfy this equality. So this is given by the Euler characteristic. That is nothing but 2 minus 2 times the number of holes of your surface. So let me, okay, so this is always the constraint that you should have on your vector fields. So what is this Euler characteristic? So if you remember from school, when you had the polyhedron, you always counted the number of vertices, you subtract the number of edges, and then you added the number of faces. And you always found this number 2. So later on, you understood that this is because the space is simply connected. So therefore, also on the sphere, you will have, again, this number 2, because if you, right, I mean, you could make your polyhedron like getting bulky, right? Or you just make a triangulation of your sphere, and again you count the number of vertices minus the number of edges and plus the number of faces, and then you will get equal to. On the torus, when you do this computation, you will get 0. Okay. And okay, so this is so this number is given by the Euler characteristic. So the genus, as I said, you should imagine that is the hole, the number of holes, or if you want, is the maximum number of cuttings that you can make on a surface, such that after cutting that, the surface still stays connected. Okay, so on a sphere, if you make a closed loop, then immediately, and you cut over there, you have 2 pieces. But on a torus, you see that, for example, if you, right, I mean, it's like on your bagel, right? If you cut it here, then, okay, it's still connected. You could feel some gem inside, yeah? Okay, so the same kind of thing, because, right, I mean, in all these models, we know that we will have a Dirichlet energy. So the same theory holds here if we put, like, finite Dirichlet energy. So if we speak in terms of H1 vector fields. So then the geometers are interested in finding what's the optimal vector field that will have the least infinite energy, right? Because we know, as I said, that if you ask that these vector fields should stay with modulus 1, like in here, and tangent, then you cannot be continuous. So something should blow up, okay? So this is mainly our question, and we will see that this comes out also in physical context. So what is the best configuration of your defects that you can put there in order that you get the least infinite energy? So there are several methodologies to study this. What you could do is, for example, to cut some disks where you impose some boundary conditions, minimize it, and then let the length of the disk go into 0. Okay, that's one methodology that will give you what you are looking at after minimizing over these cuttings. But you can also do what is done within Ginzburg-Landau methodology, is that you relax the fact that your vector field is not modulus 1, and then you penalize it in some limit when epsilon goes to 0. So this is the methodology that we will look for. So in the following, always my surfaces are what are called closed, so they are compact, connected, without boundary. And so there will be three models. In the first two models, all the order parameter is a tangent vector field, and in the other one will be a map with values in S2 where the normal component is penalized. Okay, so let's go with the first model. So we will consider here. So in 2D. In 2D, this is the easiest model. Is this called the BBH model, Bresis Bechuel Elan? So you consider this Dirichlet energy. So here U is not with values in S1, and of length 1, and that length 1 is penalized within this potential energy. So okay, but now you are on a surface. And the right notion that you have there, which is the intrinsic one, you don't need that your surface is embedded in R3, is what is called the covariant derivative. So this is given by the so-called Levi-Civita connection. Okay, let's think that we don't know what it is, and let's assume that our surface is embedded in R3. Then you should just think that you can make an extension of your vector field. You take the R3 gradient, and then you just project it to the tangent plane. Okay, that's your covariant derivative. Okay, so what do you expect? So of course this epsilon should go to 0, so that in the limit you find what you want, something with modulus 1. So these vector fields, as I said, they will have zeros. So these zeros will come with high energy when epsilon goes to 0, which is a logarithmic one. So what you do is that you take out this infinite energy, and then, so that will be at the first order, and at the second order, you expect to have the interaction between these vortices. Okay, that will give you the optimal location. Okay, so that's the first model. Let's go to the second model. So now, I suppose that my surface is isometrically embedded in R3. And again, I consider a tangent vector on that. Well, when you are embedded in R3, these are called sections of the tangent bundle, but okay, it's the same thing. And then you consider the full gradient of this tangent field. So if you remember, okay, if you remember for the covariant derivative, we projected. So in some sense, we lost the contribution of the normal component of the differential. Now you put it in. Okay. So let me make a picture. So if this is your surface, so this is embedded. So you have a normal vector. This is the Gauss map, and you take a frame, τ1, τ2. And then you have some smooth vector field there, and you differentiate it. So the differential goes out in general. So this is the bar that tells you that it will go out, M. So when you project it back into your tangent plane, then you will get this covariant derivative. So what I wrote there is nothing but this. So this is the extrinsic differential, and then And then this is, yeah, right? So what's the difference between this model and the other model is when you compute the norm of this. I don't put the metric because G will be the genus. It's nothing but the covariant plus this term that is called the shape operator. Right? Because since you are tangent, then m times nu is 0, so you can put the derivative on the other one, and you get this. Right? So this is the second fundamental form. Okay. So this is the second model. And now the third model, which is something that you will see that comes in physics, is that now, again, you will consider a 2D surface, but now you will consider maps. So it's like in the problem of the barber, yeah, with the hair. So now you consider a map that could go out of your tangent space, and then you get again the gradient squared, and then you will penalize the normal component, right? So at the end, you know that if you have enough compactness, you stay of modulus 1, and you should be in the tangent. So this term is like it's similar with the previous potential, because right, if you are on a sphere and you take m the tangential part, then the normal part is nothing but 1 minus the tangential part squared, right? And since you know that this is positive and less than 1, you get exactly this one. Okay, so this is the second extrinsic model. Okay, so what is the difference? Let's consider that we are on a cylinder, okay? So because things are easier. And you consider this constant vector, okay? So here, derivative is 0, all the derivatives are 0, right? You are constant, and you are modulus 1. But now, what you say is that, okay, but if I turn it by pi over 2 in the tangent plane, then you get this angular vector. So what's happening is that, right, so you remember that the derivative of the angular is nothing but the normal component up to a sign. Then what happens is that at the level of the intrinsic energy, when you take just the covariant derivative, you don't see any difference, so both could be minimizers. But at the level of extrinsic one, when you take also the contribution of this term, then due to this derivative, this is not the minimizer, so the minimizer will be this constant one, okay? So you expect to have changes between the models. Okay, so now some physics. So why it's not only the geometers that are interested, but also physicists. So it's good that in the previous talks we spoke a bit about ferromagnetism. So in general, how you get the model on a surface? Well, in general, you will consider a shell, and you renormalize the length. So in general, you will look to this thin film regime where the thickness is much smaller with respect to the diameter of your shell, and then this quotient you will put it tends to 0. So okay, so this is your shell, right? So you take your surface, you put some thickness, and then you will consider the easiest ferromagnetic model, where you have what is called the exchange energy, so this Dirichlet energy, and then is this non-local interaction at long range between the moments, that is the stray field potential, that will penalize the flux, the flux of your magnetization. So this is something that lives in full R3, okay? But your magnetization lives only inside your shell. So when you look to this term, you will see that this will penalize the interior divergence and the normal component. So then what will happen in this regime is that when you compute this stray field energy, in this regime, at the first order, you will penalize the normal component, okay? And the other will be some small order terms. So therefore, your stray field will come, so this is the thickness that comes out, but of course the thickness, if you consider this invariant, is also out. So if you renormalized everything, you get exactly to this model, okay? So this was done by, so of course, first in the flat is Joya James, and then a lot of people try to reproduce their argument in various contexts. So Carbu did it in some cases for the surface, and also Valeri and Giovanni work on this problem. Okay, I'm slow, but I'm slow. Okay, so okay, let me. So of course, so first time it was this kind of model, but for maps, complex functions psi. This was done by Barraquet. Okay, but he considered slightly special surfaces where you can use this uniformization theorem. So you have a Riemann conformal mapping that, in some sense, is nothing but redoing the BBH with a weight that is coming from the conformal map. Okay, you have also models in Ginzburg-Landau models where you have a magnetic domain, and so more precisely complex line bundles. And okay, what is in fact covered by our extrinsic model is this one that was so also for a thin shell. That was found by Contreras and Peter. Okay, so of course, so they started to analyze what's the first critical external field when vortices will started to appear. And then Contreras did more work on this, but on surfaces of revolution. And also, I mean, Stan and Leah work on similar contexts. But now, since we are in a nematic liquid crystal community, let me. So Apala Majumdar already mentioned this work. She mentioned in a plane surface, but so the result of Dimitri, Peter, and Montero is in general for embedded surfaces. So you take this kind of thin shell where you also put up and down some anchoring energy that. When the thickness is small, so when and this parameter delta is small, it will favors that the three eigenvectors of your Q tensor is the normal one and the two tangent ones. So it's in some sense it's similar to our problem for our extrinsic problem. And then, so this is like the continuous version for nematic shells, but also it's this discretized model that Antonio will speak after it. So together with Giacomo, they studied this discrete. So you make a triangulation, and then you discretize the Dirichlet energy, and then you will put the mesh, the size of the mesh tending to 0, so you expect to have, again, the same kind of model that I discussed. Okay, so let me tell you the results. So first of all, in this theory, the main thing is to find out the structure of the so-called harmonic unit vector field. So this is what I called the optimal least infinite energy of a vector field of modulus 1 on a surface. So that will have prescribed singularities. And as I said, the important fact is that you have these flux integrals that will be constrained on a lattice that is vortex dependent. So of course, in the flat context, these fluxes existed already if you take, for example, non-simply connected domains, like annulus or these kind of things. But in that case, these flux integrals were on a fixed lattice, no independent on your points. So this is a new phenomenon. And then once you know this harmonic unit vector field, in order to get what we call the renormalized energy, that is the interaction of your vortices, what you do is that you will cut out some small balls. You take the Dirichlet energy of this guy away from these balls, and then you make the radius go to 0. So we will deduce this interaction energy via second-order gamma convergence. And so what is the difference between the two problems? So the first problem, when we take only the covariant derivative, is that this problem is slightly like a linear problem. So Bianca already mentioned in her talk is that in the flat case, when you take S1 valued functions, then when you want to compute the Dirichlet energy, then this Dirichlet energy is nothing but the Dirichlet energy of your phase. Okay? So like this, the phase, what is good is that it's real. Okay? So like this, you linearize your problem. Okay. Then you want to understand what's happening in the more physical context where you have this extrinsic case. And the point is that these two problems are fully nonlinear, as you will see in a moment. But the importance of this intrinsic model is that this will provide you what is called the Coulomb gauge in the magnetic Ginzburg-Landau. Okay? So let's see how it goes. First of all, let me. I still have 15 minutes. Yeah. So let me recall you the dictionary about this harmonic vector fields in R2. Okay. So we take R2 and let's consider maps that are in S1 phi smooth. So the most important quantity is the so-called current. That is nothing but the gradient of your phi. So this is your current. And then the vorticity, which is the curl of your current, which in this case is 0. So nothing happens when you are smooth. Okay, but what will happen is that when you put vortices, the canonical harmonic map with singularities, with vortices ak of degree dk is this kind of guy. So here are two, I take it like the complex plane. Okay, and this phi is harmonic, is smooth and harmonic. Okay, so what is here? So when you are interested to the current, there are several ways to do it. So see, the problem is that this kind of function, if you look to the phase, it will jump. Okay. So the current represents like the absolutely continuous part of the derivative. So that's why that's a bit more complicated. But how you can do it is that, well, you could say, well, this current satisfies a system of equations that fix this current, which is when you consider the vorticity, this is a measure. This is a measure that is concentrated on those points. And the divergence is 0. Okay? So in other sense, what you have is that this current is the orthogonal gradient of the so-called conjugate harmonic. So the conjugation, the harmonic conjugate of the angle is the logarithm. Okay, so this is nothing but a function. I will explain who it is, plus the sum of logarithms. Okay, and this is what this is the harmonic conjugate of phi. So you have that gradient of phi is grad verb of psi hat. Okay, so if you want to compute this, and you take the gradient rotated by. Okay, so now within that dictionary, maybe you will understand a bit. I'm sorry, but this really hurts my ears. Okay, so first of all, you see that we are complex, right? I mean, in some sense, we need a rotation. So this is this kind of isometry that in the tangent plane will turn by pi over 2. And then the current is nothing but what I call here U wedge grad U, right? So it's nothing but this kind of scalar product, okay? And then the vorticity. So the vorticity was the curl of the current. But of course now what's happening is that you are on a surface. So the quantity that is here is given by the Gauss curvature. So the Gauss curvature is nothing but the determinant of the second fundamental form, or if you want, is the product of the sectional curvatures. Okay. So again, if you are in a place, so in a subdomain where U is smooth, then you will get that, well, this vorticity is 0, right? It's exactly like in this case, right? The vorticity is 0. So just okay. So this is the differential of this one form. So this means that here you make a curl, okay? And then we will see that also the adjoint operator will come up, and that's the divergence. So first theorem, what's this canonical vector field? So the way that we will define is the following. So let's take endpoints, so these are the vortices, that have degrees that satisfy that topological constraint that the sum is given by this Euler characteristic. Okay? Then there exists a unit vector field that satisfies, if you want, the equivalent of these two equations, provided that some conditions are fulfilled that comes from the topology. So the first one is like in the first equation there, is that the vorticity is given exactly by those points. And then, as I said, this adjoint operator that you should think in R2 like divergence is 0. So in the case where you have no holes, so you are simply connected, this fixes your solution up to a constant. But if the genus is non-zero, then you will have these flux integrals that should belong to a lattice that I will explain in the following. Okay, so these flux integrals are like counting the holes. So this is like the homology. So for example, on a torus, you should be careful what's happening on those principal curves, right? That counts one S1 and the other S1. It's a bit similar with what it was in the physical talk this morning. Okay, so how do you construct such a canonical harmonic vector field? So first of all is how do you find the right current? So what is that right current? Is the one form that satisfies this equation. So you will do exactly like in R2. You will consider this conjugate harmonic that satisfies this equation. So see here that you can always solve this because the integral of this is 0. So this is where the constraint and the sum of decay are the Euler characteristic. So here you need some Gauss-Bonnet theorem. So this will tell you that you can find this, and then what should say? Well, okay, a solution is nothing but like the gradient perp of that. So this is the adjoint operator of this second form. But then you can add some other things. So these things are so should be harmonic. Why? Because when you take the differential of the difference of this, you see that here the differential of the current satisfies this, and it's exactly d star, of course, plus d star d. So this is second, so that's 0. So this is nothing but the Laplacian. So the difference is 0. Okay. So you have that the differential of the difference is 0, and also that d star of this is 0 because d star of j is 0, and d star is 0. Okay? So that's why you have these harmonic one forms. And this is the cohomology, that is the dual of homology. We tell you that these harmonic one forms it's a space of dimension where G is the genus. So you can take a base, eta 1, eta 2G. And then this will tell you that G star is G star psi star plus the sum of some coefficients, phi L, eta L, where L goes from 1 to 2G. Okay? So now the question is, for such a solution, can you find a unit vector field that satisfies this? So this is you can solve it provided that you see these are nothing but the projections of the current on the one forms belong to a lattice. So how do you get that lattice? So if you, as I said, these are the dual of those curves, right? So for a torus, there are those two curves that will span to the homology. So what you do here is that you integrate on those curves. Okay, and then you get this. Okay, so this is a matrix that is invertible. And what's happening is that if this would be corresponding to a unit vector field, then this guy is a fixed quantity up to 2 pi. So if you take this vector, then you get that this is, so if I call alpha that matrix, times phi minus zeta, so this should be a 2 pi z2g. Okay? So these are the quantities that we are interested in. These are the flux integrals. So now you put everything there, and then this is nothing but alpha minus 1 psi plus alpha minus 1 by zeta 2g. So if you want, these flux integrals that you see will depend on the position of the vortices. 2 minutes, okay? Are nothing but this kind of distorted lattice and some translation. Okay, so then I have to hurry up. Okay, so so this is mainly what you need in order to construct it. So now let me go to how you compute this interaction energy. So suppose that you already know what's the canonical harmonic vector field that corresponds to the points and to that flux integrals. So what you do is that you cut out, you will cut off some small balls of the Dirichlet energy of this, and you take out this infinite energy. So this infinite energy is logarithmic, and then we should take this degree to the square. So this will give you the interaction energy between the vortices. So if you want to know what's the optimal position of this, you have to minimize within A, D, and phi. So, but that you can compute it
immediately by, so if you know what's the green function on your surface, then then this renormalized energy will give you this kind of logarithmic interaction between the points, and then this kind of terms that are geometrical terms, plus also the contribution of these flux integrals. So in particular, because you are interested what's happening on a sphere, so here on a sphere you will see that so on a sphere, of course, with the standard metric, the vortices will be diametrically opposed. And then, for example, if you say, okay, but that's what you expect, what's happening if you take an ellipsoid? So what's happening is that the vortices will prefer points where you have maximal curvature. So why maximal curvature? Because in some sense you want to minimize this size 0, and this means that you want to minimize the Gauss curvature, so since it's a minus there, so it's like looking to the maximum one. Okay, this is not true in general, because it's a very complicated quantity. Okay, but my time is out. But anyway, this is, so it's like reducing infinite dimension problem to this finite, right? It's, you just take finite number of points. Of course, due to this, you know that the sum is the Euler characteristic. So you know, for example, that for the sphere you should have 2 vortices of degree 1, for torus 0. But for 2 torus, for example, you should have 2 vortices of degree -1. Okay. So anyway, this is something that you can play with numerically. And of course, I didn't say what's happening for the extrinsic one, but I could answer to your question if you want to understand this gauge, this kind of Coulomb gauge. Sorry for...
Thank you.
Thanks. Always good friend, huh? To lose connections. Okay. So what changes there? So you see that when you compute this extrinsic energy, you have to add this shape operator. Okay. So it's like so you have to minimize the sum of this. So of course this is not. It's very rarely that it's the minimizer of one plus the minimizer of the other one. But you can do this using, as I said, as a Coulomb gauge, the canonical vector field. So what you need to do is that you will multiply with the rotation. This phi is a smooth function, and then when you do the computation of this in this case, you will see that this is nothing but the Dirichlet energy of this, plus the Dirichlet energy of this, plus the shape operator, plus some small terms. Okay? So this will tell you that in fact you just need to minimize this nonlinear problem in order to find the optimal rotation that you should do with respect to that one. Okay? So for example, in a sphere, nothing changes. In a sphere with the canonical metric, okay. But in general, this thing will change. So we'll give you an additional term that could change your minimizer.